Hi everyone and welcome to my presentation. First of all, let me thank that Jay Krishnan sir for compels me to do this work. Okay, as you can see on the screen, my topic is velocity of transverse wave of a stretched string. So let's begin. Let us consider coordinate x-axis and y-axis and let this red line represents the stretched string. The blue one represents the vibration of the string up and down along y-axis. Let A be any point on vibrating at an instant particle t, and with its coordinates is x and y, and B with the coordinates x plus del x, y plus del y. The tension force at the point A and B will be similar. The direction of the tension force at the point A can be given by drawing a tangent at the point A and let this tangent AT. Here T represents the tension force. Similarly, at the point B, we can give the direction of the tension force by drawing a tangent and let this be BT. Now this tangent AT makes an angle theta with respect to x-axis, so the component of the tension force at the point A can be drawn such as that. This is the horizontal component of the tension force and this is the vertical component of the tension force. Similarly, at the point B, let BT makes an angle theta 2 with respect to x-axis and let this be horizontal component at the point B and let this the vertical component. So this will be T cos theta 2 and this will be sin theta 2. So this is all about the diagram. Now let us write the statement. Let AT and BT be the two tangents at A and B making an angle theta 1 and theta 2 respectively with the x-axis. Also let tension force at A and B T. Now since the displacement at vibrating string is taking place only along y-axis and there is no displacement along x-axis, it means the horizontal component of the tension force are nullifying each other and we are only left with the vertical components. So the resultant force on this element AB is given only by these vertical components and it can be written as such that is resultant force F is equal to T sin theta 2 minus T sin theta 1. Now if our vibration is very small, that is theta 1 and theta 2 are very small, then we can write sin theta 1 equal to tan theta 1 and sin theta 2 equal to tan theta 2. Substitute this in this, we will be getting F equal to tan theta 2 minus F tan theta 1 and this is F equal to tan theta 2 minus tan theta 1. Now we know from the definition of the tension is nothing but tan theta, which is equivalent to dy by dx for this xy plane. So in place of tan theta 2 we can write this and in place of tan theta this. And thereafter in the place of del y we write this, because from the definition of the partial derivative we know that del y is equal to this. So in place of del y I have written this, and for further mathematical approach and it gives us this and here this, and this gets cancelled out and we are only left with this, and let this be equation number 1. Again, if we assume that small m represents the mass per unit length of the stretched string, then we can write mass the element AB which we have chosen, whose length is what del x is equal to mass per unit length into the length of the element del x. From the figure you can see this is the element del x of the stretched string. So from the definition of the resultant force we can write the resultant force on the element del x is equal to mass of the element. Let us tell them into double differentiation of the displacement of string along the y-axis with respect to the time, which can be further written as this. That is, in place of this del m I have written m del x from here. So this is the equation number 2. From equation 1 and 2 we can write this equal to this, and further mathematical approach will lead us to this, and further we can rearrange this and we can write it in this form. So let this be the equation number 3. Now if we compare this equation 3 with the general wave equation, as you can see here, the format is same as the equation number 3. Only the difference is what here we have v square and there we have t by m. It means what? If we compare equation 3 with this general wave equation, we get that v square equal to t by m, and that thus we get the velocity of the transverse wave. Hence, comparing equation 3 with the general wave equation, we can write the velocity at the transverse of the string is v equal to root t by m, that is tension force by mass per unit length. This is our final expression for the velocity of the transverse wave of stretched string.